Hi, I'm Yehonadav Bekenstein. In our group at the Technion, we're studying nanomaterials as a model system to better understand materials for next generation challenges. On the screen before you, you can see nanocrystals. These vials with the different bright colors are actually suspended solution of colloidal nanocrystals. They are excited with UV light and they emit very bright emission. And this emission is due to strong quantum confinement effects due to the small size of the nanocrystals. Making nanocrystals also benefits us in studying these materials. We can use TEM microscopy to see these materials with atomic resolution. And this is the second pictures you see here on the screen. We're doing all of this in order to address the next generation challenges of humanity. The energy challenge due to expansion of population and the constant demand for energy, and also addressing the information blow-up, the fact that we need to make better, smaller, and faster electronic devices. And for this, we want to understand the electronic properties of materials at the nanoscale. The methods we follow in my group is to study new materials by making colloidal nanocrystals and study these materials as these colloidal nanocrystals are the model system to better understand materials. One example I would like to give you now is of lead halide perovskites. These materials, the perovskite crystallographic structure, is known for many years, but recently people discovered that lead halide perovskites, they actually behave in a quite different way from the standard understanding. And you can see in this cartoon that this simulation of the unit cell of the perovskite is actually quite different from the static behavior people know. Things are moving all the time, bonds are breaking and forming, atoms coming in and out of the material, and all of this disorder is very counterintuitive to use this material in electronic devices. As a matter of fact, people discovered that you can actually make devices out of lead halide perovskites and get very efficient behavior. We can make solar cells, LEDs, and photodetectors with very favorable properties. And so how this is possible with such a high degree of disorder? And to answer this question, we address it through the nanoscale. We grow nanocrystals of lead halide perovskites and study and engineer their properties. And the example I want to show you here, and with this to end this very short talk, is of lead halide nanoplates. So instead of growing bulk crystals, we can actually grow very thin nanoplates with a few monolayers of these materials. And you can see in the TEM image exactly how thin these nanoplates are with atomic resolution. So growing such thin nanoplates actually changes the physical properties of these materials due to the quantum confinement effects that I mentioned earlier. And you can see the result of this in this spectroscopic image, comparing bulk perovskites, which is the red line you see here, with the nanoplates, which are now much blue shifted both in the absorption and the emission. We can also engineer other properties of these materials, and if you are interested in that, you're invited to look into my website and see the other things that we're working on. I invite you to come to the Technion and to join our group. Thank you.